All right, I am going to hand back the well, not hand them back. I will pass around the homeworks, the graded homeworks. So they're in stacks of O through Z and A through N. Again, if you can't grab your homeworks while we're in class, they're always available in the little carousel outside my office in SME. So you can pick them up anytime after that. Today we're going to finish up our introduction of multiple reactions. So we looked at the material balance on Monday. We're going to look at the energy balance today. Fortunately, the modification to the energy balance is pretty straightforward. I've shown you the modification up here. The only difference is that sum at the top. But we'll talk a little bit about how to give you some intuition about what sign that sum should be. What do we mean by the subscripts on the sum, et cetera, et cetera. Yeah? I don't have the averages yet. I do plan to pass them back on Friday, so I should be able to tell you Friday what that was. Unfortunately, one of our TAs came down with, it was like either Ebola or Zika or something awful, so we got pushed back today. Was it Ebola? It was probably Ebola. She's confirmed it was Ebola. So homework 3 is due today. Drop it off in one of these boxes up here. Homework 4 should be posted at 12:30. Homework 4 is somewhat shorter. It's only got 4 problems. It's all about multiple reactions. Actually, I don't think there's an energy balance on there, but we will need the energy balance when we get to multiple reactions with flow systems. After we spend about 20 or 25 minutes going over this bit of theory, maybe it'll only take 20, we'll get started on an example that potentially has some bonus points available for you if your team gets it done. All right, so last time when we talked about energy balances, we only had an energy balance for a single reaction. And that energy balance looked like this, which was that we said the temperature change as a function of time is equal to a ratio. And on the top of the ratio was Q, which we said was if we had a heat exchanger or something, we could either add energy or remove energy from the system. And then we had this term R sub A times, not another R, delta H times the volume of the reactor. And then on the denominator, we summed up all of the species amounts, the moles of each species, and multiplied that by their heat capacities. We saw a couple variations on this. One of them was we replaced some stuff on the bottom with the conversion X, which is a useful form if you've only got a single component, because we're typically interested in the conversion of a single component. If you have a system of more than one reaction going on, there's not really a good way to simplify this any further than that, because then you would need conversions of multiple species. And so it ends up becoming unwieldy. You end up having to dump it into MATLAB anyway. So this is usually the most straightforward way to express an energy balance. It works in this version for a single reaction because of the way that we've written the energy generation term at the top. So I just want to talk a little bit about each one of these terms. Hopefully you left a little space on top, because I am going to shift this down a little bit. Each of these terms can be understood in what they're either describing about how energy changes the temperature of the system, or the amount of energy you are putting into the system. So if you look at the Q term is the amount of energy either added to or removed from the system. Right, depending on whether or not your reactor is hotter or cooler than the jacketed fluid that you put around your reactor, that Q term can either put energy into the system or remove it from the system. We use it both ways. If the reaction is endothermic, we typically want to dump energy into the system to keep its temperature up. If it's exothermic, we typically want to cool it so it doesn't get into a runaway reaction type system. The term that's next to it this is the amount of energy either produced or consumed by the reaction itself. And so we should have some intuition about that particular term, right? If that term Well, let's think more about the reaction. If the reaction is exothermic, we would anticipate that that should contribute to raising the temperature of the system. So if we do something like that, then conceptually, we would expect that for an exothermic system, this sum, or not really the sum, that term in blue should be greater than 0. Conceptually, if it's an exothermic reaction and we are performing that reaction, we are liberating energy and we would expect the temperature to increase. If the temperature is increasing, then its derivative with respect to time is positive. If the reaction is endothermic, we would expect it to go the other way around. If it's endothermic, we expect that term to be negative, because in general, an endothermic reaction absorbs energy from its surroundings, and that tends to lower the temperature of everything. So the top two terms the two terms in the numerator are talking about where is energy coming from? Is the reaction consuming it or generating it? And are we dumping anything in from the environment? The term on the bottom is generally saying that I need such and such an amount of energy to increase the temperature of however many moles of stuff that we have by 1 degree Kelvin. Right, so that's the part that says, all right, I've got this chunk of energy that I'm giving off or sending into the system. The denominator is telling you, okay, I've got that much energy, now what's the corresponding temperature change for that much energy based on the amount of stuff that I have in the reactor. So for example, if you put a ton of inert in there, that inert is going to sit there and act as a sink for all that energy. It's not reacting, but it does require energy to increase the temperature of that inert, which is why in that sum that we have on the bottom, all the species are included. Whether or not they're reacting or not, you have to raise all of their temperatures or lower all of their temperatures. You can't pick out just species A and I only want to raise that temperature. They're all in there together, they're mixed up, and the amount of energy I need to raise the temperature of the solution for 1 degree Kelvin, for however many moles I have, is given in that term in the bottom, the green. The result then is the side on the left, which is just the temperature change. Not surprising, it's dT dt. So those are the balancing acts that we have inside any kind of a thermal system. There really isn't too many other ways that we can add or remove energy from the system. We have neglected shaft work here, but in most cases the shaft work is pretty minimal. Actually, in many cases, there is no shaft work. If you've got something like a packed bed reactor like we're going to see next week, there's nowhere to put a shaft because the thing is filled with particles. So these are the primary terms. The only one of these terms that depends on the reaction is the one in blue. The one in red is something about the environment. The one in green is something about the amount of species I have and their heat capacities. And the one in fuchsia or pink or purple, whatever we have on the left, is talking about the bulk of the reactor and how it changes with temperature. So if we increase the number of reactions that we have, the only term in here that can change is the one in blue. That one says if I have more than one reaction, I could be giving off more energy or consuming more energy just to drive that reaction. So when we switch to a multi-reaction system, the only change is that the blue term, instead of saying R sub A times delta H, this term becomes the sum of the rates of all reactions Ij times their enthalpies of reaction, delta H, Ij. So here J is summing from the first reaction up to the last reaction, and we saw in last class that we generally denote reactions as running from 1 to K. So it's a single sum. You get one of these for each one of the reactions, but that other subscript I is a little bit fuzzy. I is not a specific species in any case. It depends on how you wrote the reaction rate. So in general, if we look at the units on each one of these, the rates of I, or the rate of I, is so and so many moles of I, oh, that's a J, reacted per unit volume per unit time. The units on the enthalpy represent such and such an amount of energy release or absorbed per mole of I reacted. The reason that earlier in the course we learned that very often we normalize reaction stoichiometries to 1 is because we're used to writing these delta H's on a per mole unit basis. Right? We usually talk about per mole of A or per mole of B. If you change the stoichiometry of the system such that the stoichiometric coefficient is no longer 1, you will change delta H in a proportional way. Right? You double all the stoichiometric coefficients, you double the enthalpy of reaction. You have also changed the unit that's sitting over here. Now instead of per mole of A, it's per 2 moles of A. To avoid confusion there, because it's very easy to get that confused because usually you write your rate law as a per mole of A basis, we make that simplification for most of our stoichiometry of setting one of those species stoichiometric coefficients equal to 1. The reason that we do that is so that we don't have to worry about matching up these two units. This should also imply that the species I that you're talking about can change. Species I may only occur in some of your reactions. It may not show up in all of your reactions. You have to pick the most reasonable choice for species I. Sometimes it's easy because there's only one reacting species in each reaction. Other times you'll have to make a choice and there could be multiple ways to do the problem. As an example, by the way, I'm not going to rewrite it, but if you substitute this expression into there, that's the energy balance for a batch reacting system with multiple reactions. It's the same one that I gave on the intro slide. That's the only difference between a single reaction and a multi-reaction is this sum. So if we look at that term in a little more detail as an example, let's say we have 2 reactions going on in our reactor. The first one is A goes to B plus C. And I'm just going to use irreversible reactions right now. The procedure here doesn't change for a reversible reaction. And another one that has D goes to E. The first one, delta H of reaction 1 based on species A, we'll say this one is exothermic, so minus 10 kilojoules per mole. And we'll set the enthalpy of reaction 2 with respect to species D as, I don't know, plus 15 kilojoules per mole. So that's an endothermic reaction. Notice a couple of things that I've put a subscript on those enthalpies. Depending on what source you're getting your enthalpies from, they may or may not subscript it with respect to a particular species. If you look at equation 1, the subscript is sort of unnecessary to say it's per unit per mole of A, because there's only one reacting species, it's just A. And very frequently you won't see delta H sub 1A, you'll just see delta H sub 1, because maybe all the stoichiometric coefficients are 1, so it doesn't matter, or maybe there's only one of them and then you don't have a choice. But if you were to be explicit, then you would want to put an A on there as well. So right away, when I see that delta H1A is minus 10, that tells me, I'm going to write it down here, if I look at that term R sub ij times delta Hij, remember this is describing, if you look in the energy balance, I'm going to flip back one, this is one of those blue terms, so I know if that blue term is positive, I would normally expect an exothermic reaction because that's going to increase the temperature of my reactor. So right away when I see delta H of minus 10 kilojoules per mole, I know that's an exothermic reaction. And whatever I write next, I would expect, however I write R sub 1A delta H sub 1A, this entire term had better be greater than 0. It's an exothermic reaction, it's giving off energy. If the reaction is proceeding, I would expect the derivative of temperature with respect to time to be positive. Similarly, when I see that one of those enthalpies is positive, the one for reaction 2, I know that when I write the rate of reaction for species or reaction 2 with respect to species D times its enthalpy, I expect that term to be less than 0, because that's an endothermic reaction, which generally tends to drive the temperature of the system down. This is one way that you can try to catch mistakes on your MATLAB code, which is that if it runs and it seems to run forever, try stopping it partway through its run. There's a little pause button up there, and investigate the sign of dt. Right? If you're playing around with what's that called? Not the breakpoint editor, the debugger, where you're hitting pause or something, you can evaluate the slope of temperature with respect to time, this dt term, at every step of the calculation. And you can watch it and make sure, is this thing going positive or is it going negative? And use a little bit of engineering judgment based on whether the reaction is exothermic or endothermic to decide if you've made a sign error somewhere. So if your temperatures are blowing up to 1,000,000 and you're supposed to have an endothermic reaction, that's kind of a problem that suggests you have a sign error. So this is this is a good level of intuition that you can use when you're coding these things in MATLAB, is to just check signs, make sure those are consistent. So if I wanted to write that full term of the sum of R sub ij times delta H of ij, this is going to look like the following. I get R sub 1a delta H 1a plus R sub 2d times delta H of 2d. And that entire term goes into our energy balance, the sum of which is multiplied by volume to get that total energy. Now I can investigate the signs a little bit. If I write R sub 1a, remember the way that we usually write this is with a minus sign in front. That would just be equal to K of reaction 1 times C sub A. Again, just like the enthalpies sometimes drop the species identifier, usually the Ks are written for a single reaction. Technically that is with respect to species A, but we usually don't include that because the choice of species is usually not important, because stoichiometric coefficients tend to be removed. So we have R sub 1a is equal to K1Ca with a negative sign, which means if I investigate the signs on each one of these, this one I would expect to be negative. Right? A is a reactant. I would assume that if this thing is proceeding, that reaction is going to consume A, so R1a is negative. From the problem statement, it's also exothermic, so my next term, delta H1a, is also negative. And the net result is that this entire term is positive. So I've double-checked that the way that I will write a rate law, which is usually minus R is equal to some factor K times some function of concentrations, is going to overall give me a positive value. So in general, the first reaction is going to tend to drive the temperature of the system up. It's going to make that slope positive. If you compare it to the second reaction, R2D, 2, is equal to, no, that's just going to confuse somebody if they're reading this later and they don't get the joke. Is equal to K2 times the concentration of species D. Right? In general, that reaction, if it proceeds, species D is going to get consumed by that reaction. And so this is overall going to be a negative term. And if I compare the signs here, R2D is going to be negative. According to the problem statement, the enthalpy of reaction of species 2 per mole of D is a positive number. So this is positive, and the overall contribution of reaction 2 is to drive down the temperature of the reactor. Right, which matches our intuition of an endothermic reaction. An endothermic reaction, we typically have to dump energy into it because the reaction itself is consuming that energy. Well, I mean, technically it's not consuming, but you know what I mean. Whereas reaction 1 is giving off energy. And there's no reason when you have a system of multiple reactions that you would expect the net effect of the reactor temperature to go up or down. If some of the reactions are headed up and some of the reactions are headed down, it's very difficult to anticipate before solving the problem what the net effect is of those two reactions on the temperature of the reactor. The reason being their rates are typically not equal. So at some points in time, the rates of the exothermic might be higher, and so the temperature goes up. That one might approach equilibrium, and then the endothermic one kicks in and the temperature of the reactor goes back down. There's not really a way to predict that behavior until you solve the problem. But this is about as far as we can go to check our intuition based on a problem statement of saying an exothermic should raise the temperature and an endothermic should lower the temperature. After this point, that's the only modification for the energy balance. The rest of the energy balance looks the same as for a single reaction. This tends to have to be coupled with all of the material balances. The reason we have to couple it with all of the material balances and not just one is because we have no way to simplify that term in green down here on the bottom. We can't really write that in terms of conversion of a single species because, as we just saw, there can be examples of reactions where the same species is not a reactant in all of the reactions. So it's very difficult to write anything simplified in terms of conversion of a single species. Therefore, typically what we need to do if we want to know the conversion of a species is to solve the entire system for either the moles or the concentrations of everything and the temperature, both as a function of time, and then calculate x based on that data. Right? When we solve that system in MATLAB with ODE 45 or something, we get this big vector of data of moles as a function of time or temperature as a function of time, and we just take that data and calculate x directly. So for example, if we wanted to know the final conversion after some time t, the conversion of any species A at any time t, actually let's just say not A, I, doesn't have to be A now, is the moles of species that you started with, so moles of I 0, minus the moles of I at any time t, divided by the moles of I that you started with. It's very hard to put an expression like that into either the energy balance or the material balances when you have more than one reaction, so we typically don't. If we need to know that value, we solve the system to get all of the n's and then calculate the x's afterwards, after we're all done. Similarly, you would have to do the same thing if you needed to calculate, for example, the selectivity of a desired component to an undesired component, or the yield of a desired component. Right? Any of those terms, we typically start off by just solving the system for all of the n's and the temperature as a function of time, and then calculating those values after we're done solving the system. All of those equations are quite difficult to incorporate into the energy and material balances, so it's usually not worth the headache. Any questions on how we approach energy balances for multi-reactions? Yeah.
So the last lecture we learned how to get the number of moles as a function of time. We have multiple reactions. If we have that with the temperature as a function of time, and so we can just pull the data whenever we want to get the conversion, can we just plug this into MATLAB as well and say once you grab all that data, compute this after you're done too?
Yep. Okay. So typically what you'll see is the first 3 lines of your solution script don't change. You define the time span that you're interested in, the initial conditions, and then you solve it with ODE 45. Right after that line, if you need x or s or y or something, you'd say, okay, x is equal to one of these columns of y divided by the initial value of y. So it's usually a 1 or 2 line calculation after the ODE 45 statement.
Okay.
Which is simply because you don't know any of the moles until after ODE 45 tells you what they are. So most of your code looks the same, right? You've added a reaction, you've added a couple of rates or something like that, but that ODE function file that you have on the bottom, the fundamental form of that doesn't change just because x or s or y has to be calculated. We always solve these things by determining all of the moles and the temperature and then calculating those after the fact, rather than trying to do it as we go. Any other questions? Nada? All right, so today and tomorrow we're going to, or not tomorrow, Friday, we're going to practice these things. It is, I mean, sometimes I've slammed my hand in a door and thought it more enjoyable than watching someone code, but it's not very often. I think watching somebody code up here is pretty boring. So I will try to come up with as many different ways of not just standing up here coding problems as I can. So I've got a problem statement that I want you to break into groups of no more than 3. So let me describe this before you get into groups of 3. Who's heard of a code snippet? Anybody heard of the word code snippet? If you're looking for like how to do a piece of code or something and you Google it, usually there'll be a little chunk of code, but not the whole code. That's called a code snippet. So I have a problem statement here, which is a multi-reaction system. It's actually pretty common. This is called thermal cracking. So any of your petroleum products typically start from a barrel of oil that has hydrocarbons of different length, and we need to chop those up into manageable lengths. This is an example of a few of those reactions. I've given you all the reaction information and the species information underneath it, and then I've given you a short problem statement underneath and asked you to write the code for it. I have given you the code. The code is in these baggies. This is the correct code for solving almost any system of multiple reactions. I have vectorized the code a little bit to make it easier to read. It's your job with your team to assemble the code. If you assemble the code correctly, I have tape here. I want you to tape your code on the back. If you assemble the code correctly and I take it back to my office and it runs and gives the right answer, I will give your team +2 points on the multi-reaction homework. So instead of like 10 out of 10, you can get 12 out of 10 for that homework. What I would like you to do, because I have given you the MATLAB code, right? I want you to be less worried about how is it he managed to put all the heat capacities into a single vector and calculate that value. And I want you to focus more on what did he calculate and when. Why did he structure the code the way that he did? It's going to look the same as that code I gave as an example before, where you have to start with constants and then explicit equations and then differentials. Why did I structure it the way that I did? And pay attention to the units. So I want you, after each line, you can scribble in the units of the value that was just calculated. These are the general tools that we use when we're trying to troubleshoot what went wrong with our code. It's typically not a syntax error, right? Just because you don't know how I vectorized the code doesn't mean that you couldn't write it one line at a time and get the same answer. So worry less about the syntax and more about the structure of the code, because that's the same structure you're going to have to use on all of these multi-reaction problems. So again, groups of no more than 3. I only have 30 of these, so if there's, typically we don't have a full set of 100 students in here, so we should be okay. But teams of 3, I can't have you work individually because I don't have enough copies of this, because I literally had to slice up 29 lines of code 30 different times, and I get tired of doing that. So get into your groups. Please have one person raise your hand. One person from your team, I will give that person your code. All right, just before you get working, can I have your attention real quick? I left something off of the problem statement. Guys, there is something missing from the problem statement, so you'll want to be quiet for a moment. The one thing that is missing from this problem statement that should be there, it was handled in the code, I forgot to add it to the problem statement, is that initially the total number of moles is 1,000. Right, you'll find a strip of the code that defines the initial ones with respect to 1,000 moles. I forgot to write that on the problem statement itself. When you think your code is done, raise your hand. I've got some tape up here. I'll throw a roll of tape to your team, and you can tape your code down. Yep. Also, I'm going to wander around. If you guys have questions, feel free to raise your hand and I'll answer.